Welcome to Quietly Made. I am so glad you have found your way here tonight. This is a space for the curious and the weary, a place where we explore the vast, invisible infrastructures of our world, while giving your mind the permission it needs to simply rest. Before we begin, I invite you to join our community by subscribing and leaving a comment. I often wonder where these stories find you tonight. If you feel inclined, please leave a comment sharing what part of the world you are in and the hour you are settling into sleep. It is a small way for us to feel the quiet connection of this community, scattered across different time zones, but sharing this same moment of rest. If you fall asleep, that is exactly what should happen. You are safe here. You can always come back tomorrow and pick up exactly where you left off. Adjust your pillow. Take a deep, slow breath in and let it out. Let your mind drift as we begin. Tonight, we turn our attention to the quiet assembly of the global positioning system, to the constellation of satellites tracing paths 12,000 miles above your head, broadcasting timestamps with billionth of a second precision, to the engineers who understood that knowing when something happens is the same as knowing where it is, that 4 clocks in the sky could tell you your position on Earth to within arm's reach. This is not a story of instant navigation. It is a story of patient triangulation, of atomic clocks that drift by nanoseconds and must be corrected from the ground, of signals so weak they arrive at your device 1,000 times fainter than the whisper of distant starlight. It is a story written in the language of relativity and radio waves, in the hum of cesium oscillators and the silent choreography of satellites that never waver from their invisible rails. We begin not with a map, but with a question that troubled navigators for centuries. How do you know where you are when every landmark has vanished from sight? The ocean offered no fixed points. A ship far from shore had only the sun, the stars, the magnetic compass, tools that gave partial answers but never complete certainty. Latitude could be measured by observing the sun's height at noon, by measuring the angle of Polaris above the horizon. This was geometry, reliable, practiced since ancient times. Longitude was harder. It required knowing time. The Earth rotates 15 degrees per hour. So if you knew the time at a reference point, Greenwich, for instance, and could compare it to local time where you stood, the difference in hours multiplied by 15 gave your longitude. Simple in principle, impossible in practice, without accurate clocks. A pendulum clock keeps good time on land, but fails at sea where the ship's motion disturbs the swing. Spring-driven chronometers were developed, mechanical marvels that could maintain time across weeks of voyage despite temperature changes, despite the constant motion of a ship in waves. These chronometers were expensive, fragile, required careful winding, but they worked well enough to enable navigation with accuracy measured in miles. This was the state of navigation for centuries. Sun sights and chronometers, dead reckoning between position fixes, accumulated errors that meant ships sometimes found themselves leagues from where they believed they were. Dangerous near coastlines, potentially fatal in combat. Radio offered new possibilities. A transmitter at a known location could send a signal. A receiver could detect that signal, could measure some property of it, could infer something about distance or direction. Early systems used directional antennas to determine the bearing to a transmitter. Crossing bearings from two stations gave a position fix, crude but useful. The distance to a transmitter could be measured if the signal's travel time was known. Radio waves move at the speed of light, about 1 foot per nanosecond, about 1,000 feet per microsecond. If a transmitter broadcast a timed pulse and a receiver could measure when it arrived, the delay multiplied by the speed of light gave distance. But this required synchronization. The transmitter and receiver needed to agree on what time it was to measure the delay accurately. Carrying synchronized clocks was impractical for moving receivers. The solution was to use multiple transmitters to compare the difference in arrival times from different sources. Hyperbolic navigation systems worked this way. Two transmitters broadcast synchronized pulses. A receiver measured the time difference between arrivals. That time difference corresponded to a curve, a hyperbola, of points equidistant from the two transmitters. Adding a third transmitter gave a second hyperbola. The intersection of these curves was the receiver's position. These systems were implemented using chains of ground-based transmitters spaced hundreds of miles apart. They worked, covering ocean basins, allowing ships and aircraft to navigate even when weather obscured celestial observations. But they required extensive infrastructure, were vulnerable to interference, had coverage gaps, suffered from atmospheric effects that degraded accuracy. The notion of satellite navigation emerged from several insights. Satellites orbited predictably, their positions calculable with extraordinary precision. A receiver that could determine its distance from several satellites whose positions were known could triangulate its location. The mathematics were straightforward. 3 distances to 3 known points defined a position in 3-dimensional space. But measuring distance to a satellite required timing. Light travels roughly 1 foot per nanosecond. To measure distance with accuracy of 10 feet required timing precision of 10 nanoseconds. To achieve meter-level accuracy required nanosecond precision. This level of timing demanded atomic clocks, devices where time was defined not by mechanical oscillations, but by the frequency of electromagnetic radiation emitted or absorbed by atoms in specific quantum transitions. Cesium clocks used the transition frequency of cesium atoms between 2 hyperfine states, a frequency of roughly 9 billion cycles per second, defined with such precision that measuring it for 1 second gave time accuracy to billionths of a second. These clocks were large, delicate, power-hungry, but they could be placed on satellites where size and power were manageable. A satellite carrying an atomic clock could broadcast a signal encoding the time according to its clock. A receiver on Earth, receiving signals from multiple satellites, could compare the arrival times, could calculate the differences, could, from those differences, determine its position. If the receiver also had an atomic clock to compare against. But putting atomic clocks in receivers was impractical for widespread use. The clocks were expensive, too large for handheld devices, required maintenance. The solution was clever. Use the satellites themselves to provide timing, to turn the user's unknown clock error into another variable to solve for. With 4 satellites, a receiver could determine 4 unknowns, 3 spatial coordinates, and its own clock offset from satellite time. The mathematics required solving 4 equations in 4 unknowns, determining where in space and when in time the receiver existed, such that the signals from 4 satellites arrived with the observed delays. This meant that the positioning system provided time as well as location. A receiver anywhere on Earth, receiving signals from satellites, could determine not just where it was, but what time it was, synchronized to the master clocks in orbit to within nanoseconds. This timing capability would prove as valuable as the positioning itself, enabling synchronization of telecommunications networks, financial transactions, power grids. The satellites themselves were engineering exercises in reliability and precision. They had to maintain their orbits for years without attention, had to survive the radiation environment of space, had to keep their clocks stable despite temperature variations, despite the gradual degradation of components exposed to vacuum and cosmic rays. The orbits were chosen to ensure coverage. At least 4 satellites visible from any point on Earth at any time. This required a constellation of 24 satellites, arranged in orbital planes inclined to the equator, at altitudes of roughly 12,000 miles. At this altitude, the satellites completed 2 orbits per day, their positions repeating each day, their ground tracks tracing the same paths. Maintaining these orbits required occasional adjustments. Gravitational perturbations from the Moon, from the Sun, from the irregular shape of the Earth caused the orbits to drift slowly. Thruster firings corrected these drifts, nudging satellites back to their assigned positions. The fuel for these corrections was finite, determining satellite lifetime, ultimately requiring replacement when maneuvering fuel was exhausted. The signals broadcast by satellites were carefully designed. Each satellite transmitted on the same frequencies, but with unique codes, pseudo-random sequences of ones and zeros that repeated with periods of milliseconds. The receiver, knowing these codes, could correlate the incoming signal against expected patterns, could identify which satellite was transmitting, could determine the time offset between when the code was transmitted and when it was received. The codes were chosen to have low cross-correlation. Listening for one satellite's code would not be confused by signals from others. This allowed all satellites to share the same frequencies, simplifying receiver design using spectrum efficiently. The codes also spread the signal power across wide bandwidths, making the signals resistant to jamming, resistant to interference from other radio sources. The signal strength at the ground was extraordinarily weak. After traveling 12,000 miles, spreading across the expanding spherical wavefront, the signal power at a receiver was measured in femtowatts, millionths of billionths of a watt. This was below the thermal noise floor, below the random electromagnetic fluctuations present in any receiver. Yet the signals could be extracted through correlation. By multiplying the incoming signal by a locally generated replica of the expected code and integrating over time, the receiver could pull the signal out of noise, could accumulate enough signal energy to detect the pattern, to measure the time offset. This processing gain, the ratio of bandwidth to data rate, allowed detection of signals buried deep in noise. The satellites broadcast more than just codes. They transmitted navigation messages, data streams encoding their own positions, the health of their systems, corrections for atmospheric delays, parameters for converting satellite time to universal time. The navigation message was encoded at low data rates, 50 bits per second, chosen to be robust, reliably decodable, even with weak signals. Decoding the navigation message took time. The full message repeated every 12.5 minutes, containing orbital parameters for all satellites, almanac data allowing the receiver to know which satellites were available, where they were. A receiver starting from complete ignorance, a cold start, needed to collect this data before it could compute positions, meaning first position fixes took minutes. Once a receiver had the navigation message, had its own approximate position, subsequent fixes were faster. The receiver knew which satellites to expect, where to look for their signals, could acquire them quickly, could compute positions within seconds. But initial acquisition, that first lock after being powered off for extended periods, remained slow. The position calculated by a receiver was only as accurate as its knowledge of satellite positions and the signal propagation delays. Satellite positions were predicted using orbital models, updated periodically based on tracking data from ground stations. The predictions were accurate, but not perfect. Errors of a few meters accumulated over hours between updates. Signal propagation delays were affected by the atmosphere. The ionosphere, a layer of electrically charged particles extending from roughly 50 to 600 miles altitude, slowed radio waves, the delay dependent on the density of free electrons along the signal path. This density varied with time of day, with solar activity, with geographic location. The satellites broadcast on two frequencies specifically to allow correction of ionospheric delay. The ionosphere affects different frequencies differently, the delay inversely proportional to frequency squared. By measuring the delay difference between two frequencies, a receiver could calculate the ionospheric contribution and remove it from the distance measurement. The troposphere, the lower atmosphere where weather occurs, also slowed signals, but this delay did not vary with frequency, so dual frequency measurements could not remove it. Instead, models predicted tropospheric delay based on temperature, pressure, humidity, parameters that could be measured or estimated. The models were imperfect, contributing error of decimeters to positions. Multipath was another error source. Signals reflecting off buildings, off the ground, off vehicles, arrived at the receiver, delayed relative to the direct signal. If the direct signal and reflected signal were similar in strength, the receiver might track a combination, introducing errors. Anti-multipath techniques, using antenna designs that rejected signals from below, using signal processing to identify and reject reflections, mitigated but did not eliminate this. The accuracy achievable depended on many factors. With clear sky views, with good satellite geometry, with modern receivers and correction data, positions could be determined to within a few meters horizontally, somewhat worse vertically. Vertical accuracy suffered because satellites were all above the receiver, providing poor geometric diversity in the vertical dimension. Differential techniques improved accuracy significantly. A reference receiver at a known location could measure the errors in its own position fixes, could broadcast corrections for satellite clock errors, for orbital errors, for atmospheric delays. Nearby receivers applying these corrections achieved accuracies of meters or better. The residual errors, dominated by local effects like multipath that varied between receivers. Real-time kinematic positioning, using carrier phase measurements rather than code measurements, could achieve centimeter-level accuracy. The carrier wave, the underlying radio frequency, oscillated roughly 1,500 times per code chip. Measuring the phase of this carrier to fractions of a cycle allowed distance measurements with millimeter precision. But carrier phase was ambiguous. The receiver knew the fractional phase, but not how many full cycles had elapsed during signal travel. Resolving this integer ambiguity required sophisticated processing, often requiring minutes of stationary observation, or relative positioning between two receivers sharing common satellites where ambiguities could be differenced away. These high-precision techniques required expensive equipment, careful procedure, post-processing. They served surveying, precision agriculture, geophysical measurements. For most users, the standard code-based positioning with meter-level accuracy was sufficient, enabling car navigation, location-based services, emergency response. The military origins of the system shaped its architecture in fundamental ways. The satellites broadcast two types of signals: a coarse acquisition signal available to all users, and an encrypted precise signal available only to military receivers with the correct cryptographic keys. The precise signal used a different code structure, higher chipping rate, providing inherently better ranging accuracy. But even without the precise signal, clever processing of the core signal could achieve accuracies approaching those of the precise signal, diminishing the military advantage. Selective availability was implemented to degrade accuracy for civilian users intentionally, introducing errors into the satellite clock and orbital data broadcast on the civilian signal. This reduced accuracy from meters to tens of meters, preserving military advantage while allowing widespread civilian use. The degradation was achieved through carefully controlled dithering of clock and ephemeris parameters. The military receivers, having access to precise data from alternate channels, were not affected. Civilian receivers saw the corrupted data and computed degraded positions. This policy persisted for years but became increasingly untenable as civilian reliance on the system grew, as differential techniques allowed users to work around the degradation as economic and political pressures mounted. Eventually, selective availability was discontinued. the civilian signal allowed to achieve its full inherent accuracy. The decision reflected recognition that denying accuracy to adversaries was impractical when they could establish reference stations, could use differential techniques, could exploit the same physics available to anyone. Better to allow full civilian utility while developing other means of denying hostile use during conflicts. Jamming remained a concern. The signals were so weak that modest transmitter power on the same frequencies could overwhelm them locally. Military receivers incorporated anti-jam techniques, directional antennas that could null out interference, spread spectrum processing that extracted signals from jamming, encrypted signals resistant to spoofing. Civilian receivers had fewer protections. Strong interference could deny service. Spoofing, transmitting false signals that mimicked real satellite signals, could mislead receivers, causing them to compute incorrect positions. This was demonstrated in controlled tests, showing that unsophisticated receivers could be deceived. Authentication mechanisms were developed to allow receivers to verify signal authenticity, to detect spoofing attempts. These involved cryptographic signatures embedded in navigation messages, verifiable only by receivers with appropriate keys. Implementation was gradual, backward compatibility with legacy receivers complicating rollout. The vulnerability of a system now embedded in critical infrastructure, navigation, timing for telecommunications, power grid synchronization, financial transactions, drove efforts to increase resilience, to provide backup systems, to harden receivers against interference. Alternative positioning systems were developed by other nations, partly for independence from a system controlled by another country's military, partly for strategic advantage. These constellations use similar principles: satellites broadcasting timed signals, receivers triangulating from multiple sources, but with different orbital configurations, different signal structures, different management. Receivers that could use multiple constellations increased availability, improved accuracy through better satellite geometry, provided redundancy if one system was denied. But they also increased complexity, required processing more signals, managing more orbital data, reconciling timescales, and coordinate systems between systems. The transformation of what began as a military navigation tool into a global utility was neither planned nor fully anticipated. Early projections underestimated civilian demand, did not foresee how rapidly the technology would miniaturize, how cheaply receivers could be manufactured, how many applications would emerge. Car navigation was perhaps predictable. Drivers wanting to know their location, wanting routing assistance, wanting to avoid getting lost. But the integration into smartphones, making positioning available to billions, enabling location-based services, geosocial applications, augmented reality, was transformative in scope. Agriculture adopted precision positioning for automated steering of tractors, for variable rate application of fertilizers and pesticides based on precise location, for mapping fields and yields with meter-scale resolution. This improved efficiency, reduced environmental impact, increased productivity. Aviation used the system for navigation, for precision approaches to airports, eventually for automatic landings in low visibility. The timing signals synchronized air traffic control systems, enabled precise spacing of aircraft, improved safety and capacity. Maritime navigation was enhanced beyond traditional methods, allowing ships to navigate narrow channels, to locate fishing grounds, to conduct search and rescue operations. The system was mandated for various classes of vessels, integrated into bridge electronics, backed up by traditional navigation as redundancy. Surveying and mapping were revolutionized, allowing rapid establishment of control points, precise measurement of distances and areas, creation of geographic databases with unprecedented detail. The technology enabled monitoring of tectonic motion, subsidence, glacial movement, providing data for geophysical research. Timing applications proved as important as positioning. Telecommunications networks used the timing signals to synchronize cell towers, ensuring handoffs between towers occurred seamlessly. Power grids used precise time to coordinate protective relays, to timestamp disturbances, to manage interconnections between regional grids. Financial markets relied on timestamps for transaction ordering, for regulatory compliance, for fraud detection. Scientific experiments required synchronization across distributed instruments, precise time tags for events observed at multiple locations. The receivers themselves evolved from equipment requiring racks of electronics, consuming hundreds of watts, costing tens of thousands, to chips smaller than a thumbnail, consuming milliwatts, costing a few dollars. This miniaturization paralleled broader semiconductor advances, but also reflected receiver-specific innovations. Early receivers processed signals using analog techniques, requiring careful tuning, temperature compensation, shielding from interference. Digital processing, using dedicated signal processors or general-purpose processors running specialized software, allowed flexible implementation, easy updates, integration of advanced algorithms. The shift to software-defined receivers meant that much of the receiver functionality existed as code rather than hardware. New signals could be accommodated through software updates rather than hardware replacement. Algorithms could be improved without changing the physical device. Antenna design progressed from large, helical or patch antennas requiring clear ground planes to compact ceramic antennas that could be embedded in plastic cases. Performance improved through better materials, better modeling of antenna patterns, integration with receiver electronics to compensate for antenna limitations. Power consumption decreased through multiple generations of semiconductor process technology, through architectural optimizations that reduced computation, through clever use of intermittent operation, acquiring signals, computing position, then sleeping until the next update was needed. The integration into smartphones drove specifications that standalone receivers never faced. The antenna had to work inside a metal frame device filled with other radios, cellular, Wi-Fi, Bluetooth, all potential interferers. The receiver had to operate in dense urban environments with limited sky views. with massive multipath. It had to achieve fixes quickly, within seconds, to serve applications like mapping or location sharing. Assisted positioning techniques used cellular networks to provide initial position estimates, satellite almanacs, time synchronization, allowing receivers to achieve faster first fixes. The network could also offload computational load from the device, sending satellite positions and measurements to servers that computed positions and returned results. This raised privacy concerns. The network learned the device's position, potentially tracking users without their knowledge or consent. Policies and technologies to protect location privacy became necessary, allowing users to control when and how their location was shared, providing options for on-device computation when privacy was paramount. The accuracy demands of various applications pushed development of augmentation systems. Aviation required approach guidance with vertical accuracy of meters, with integrity monitoring to detect faults within seconds. Autonomous vehicles needed lane-level positioning with decimeter accuracy, updated multiple times per second. Satellite-based augmentation systems use geostationary satellites to broadcast correction data, differential corrections, improving accuracy, integrity messages, warning of satellite failures, ionospheric models improving delay estimates. Ground stations monitored satellite signals, computed corrections, uploaded them to the geostationary satellites for broadcast. Ground-based augmentation systems used local reference stations around airports, providing corrections specific to that region, achieving the precision needed for Category 3 approaches where aircraft could land in visibility so poor the pilots could not see the runway until seconds before touchdown. These augmentation systems represented substantial infrastructure investments, certified to aviation safety standards, monitored continuously, maintained with redundancy, ensuring continuous availability. They demonstrated that while the basic positioning system was free to use, achieving the performance required for critical applications required additional investment. The evolution of satellite technology enabled new capabilities. Early satellites were bus-sized structures weighing hundreds of kilograms, designed for 10-year lifespans, launched individually on dedicated rockets. Later generations increased power, improved clocks, added signals, while reducing mass and extending lifetimes. The atomic clocks aboard satellites improved from rubidium standards with stabilities of parts in 10 trillion to hydrogen masses and advanced rubidium clocks approaching parts in 10 quadrillion. Better clocks meant more accurate ranging, less need for ground updates, longer intervals between satellite maintenance. Additional signals were added on new frequencies, providing more measurements for ionospheric correction, improving multipath resistance, offering specialized signals for different user communities. The signal structures incorporated features learned from decades of operation: forward error correction for the navigation message, spreading codes chosen for better correlation properties, pilot signals to assist receiver acquisition. Inter-satellite links allowed satellites to communicate with each other, to share timing, to enable autonomous operation when ground contact was lost. This improved system resilience, reduced dependence on globally distributed ground stations, enabled operation in scenarios where terrestrial infrastructure was compromised. The next generation of satellites incorporated completely new signal designs, exploiting modern digital signal processing capabilities, providing better performance in challenging environments, urban canyons, indoors, under foliage. The signals were designed with lessons from interference incidents, from jamming demonstrations, from decades of user feedback about where the system struggled. Modernization faced the challenge of backward compatibility. Billions of existing receivers could only process the legacy signals. New signals had to coexist with old, sharing spectrum without interfering, allowing gradual transition as old receivers were replaced. This constrained design choices, limiting how radically signals could be improved. The ground control segment evolved from a few monitoring stations to a globally distributed network, tracking satellites continuously, uploading navigation messages multiple times per day, monitoring satellite health, managing the constellation. The operations were largely automated, with operators supervising rather than manually commanding satellites. Predictive maintenance used telemetry from satellites to identify degrading components before failure, to schedule replacements that minimized service disruptions. Redundancy in critical subsystems, clocks, transmitters, attitude control, allowed satellites to continue operating despite failures, extending their useful lives. The replacement strategy balanced cost against capability and risk. Launching satellites before old ones failed maintained constellation strength, but required investment before absolutely necessary. Waiting until failures occurred risked service degradation if launches were delayed. The balance shifted as launch costs changed, as satellite reliability improved, as user dependencies increased. The commercial space sector's growth enabled new approaches. Small satellites in lower orbits could augment the primary constellation, providing additional signals, potentially offering faster updates, enabling new services. Lower orbits meant stronger signals, faster satellite motion relative to the ground, different error characteristics. But lower orbits also meant shorter satellite lifetimes from atmospheric drag, required more satellites to maintain coverage, complicated receiver design with more Doppler shift. Whether low orbit augmentation would prove valuable depended on services offered, on whether signal strength advantages outweighed complexity. Private augmentation services emerged, selling premium corrections, guaranteed availability, customer support. These served industries where reliability justified subscription costs: agriculture, surveying, maritime operations. The business model depended on providing value beyond the free baseline service through better accuracy, better integrity monitoring, better customer experience. The ecosystem around positioning included not just satellites and receivers, but also correction services, software applications, integration platforms, professional services for installation and support. The economic value of this ecosystem far exceeded the cost of the satellite system itself, creating constituencies invested in system continuation and improvement. The question of who pays for the satellite system remained complex. Taxpayers funded development and operation through military budgets, yet most use was civilian. International users benefited without contributing to costs, though reciprocal agreements provided access to other nations' systems. Cost-sharing proposals faced challenges: how to apportion costs fairly, how to maintain open access while recovering expenses, how to avoid fragmenting the global system into incompatible regional services. The balance between public good and cost recovery remained unresolved, handled differently in different countries. The fundamental physics underlying positioning set limits on achievable accuracy. The speed of light was fixed, determining how precisely distance could be measured from timing. The orbital dynamics were deterministic but perturbed by factors: solar radiation pressure, atmospheric drag, gravitational anomalies that could not be perfectly modeled. Atmospheric effects introduced delays that varied unpredictably, were influenced by weather, by solar activity, by time of day. Receiver noise, quantization errors, processing limitations added uncertainty. Multipath in complex environments created systematic errors resistant to simple mitigation. Achieving meter-level accuracy with the standard service was straightforward in open environments. Achieving decimeter accuracy required differential corrections or carrier phase processing. Achieving centimeter accuracy required high-quality equipment, careful methodology, post-processing, favorable conditions. Achieving millimeter accuracy pushed into the realm of specialized geodetic applications with extended observation times. Each order of magnitude improvement in accuracy required roughly an order of magnitude more complexity, cost, and effort. The system served different user communities along this spectrum, from casual hikers needing 100-meter accuracy, through drivers needing lane-level 5-meter accuracy, to surveyors needing centimeter accuracy. The diversity of requirements meant no single solution suited everyone. The architecture provided a baseline accessible to all, with augmentation paths for those needing better performance. This flexibility was strength, allowing the system to serve billions while meeting specialized demands. Reflections on dependence emerged as outages or disruptions occurred. Solar flares occasionally degraded signals. Satellites failed, reducing constellation strength. Interference, accidental from television transmitters, deliberate from military exercises, denied service locally. Each incident reminded users of their reliance, of the vulnerability inherent in depending on infrastructure they did not control. Backup navigation systems were recommended for critical applications. Inertial navigation systems that tracked position from accelerometer and gyroscope measurements. Dead reckoning that estimated position from speed and heading. Celestial navigation that used traditional methods. But these backups were often neglected, expensive, unfamiliar to operators trained on satellite positioning. The generation of navigators who learned traditional methods was aging, retiring, taking their knowledge with them. Younger operators, having always had satellite positioning, often lacked proficiency in alternatives. This created risk. If the satellite system failed for extended periods, navigation capability might be severely degraded until alternative methods could be relearned or new systems deployed. Resilience strategies included diversifying sources, using multiple satellite constellations, integrating positioning with other sensors, maintaining capability in multiple navigation methods. But these added cost, complexity, training requirements. The trade-off between resilience and efficiency was ongoing, resolved differently across applications. The philosophical implications of positioning technology were subtle but profound. The ability to know one's location precisely at any moment changed the experience of space, of navigation, of exploration. The uncertainty that once accompanied travel, where am I? How far to the destination? What route is best? Was largely eliminated. This was liberating, reducing anxiety, enabling efficiency, opening possibilities for travel to unfamiliar places. But it also diminished certain experiences. The satisfaction of navigating successfully using maps and landmarks. The attentiveness required when navigation demanded focus. The adventure of accepting uncertainty. The technology mediated the relationship between person and place. Position was no longer determined through engagement with the environment, observing terrain, reading signs, asking directions, but through reception of signals from satellites invisible overhead. The place became coordinates. The route became a line on a screen. The journey became progress toward a waypoint. Whether this was gain or loss depended on values, on what aspects of navigation were deemed important. Efficiency favored technology, connection to place, development of navigational intuition, self-reliance favored traditional methods. Most people use technology reflexively, enjoying benefits without reflecting on costs. The tracking capability enabled by continuous positioning raised surveillance concerns. Devices that knew their location could report it, creating records of movements, of places visited, of patterns of life. This data was valuable for traffic management, for targeted advertising, for law enforcement, for understanding human behavior at scale. But it was also sensitive. Location history could reveal medical visits, political activities, religious practices, relationships. The accumulation of this data by corporations or governments created power asymmetries, risks of misuse, chilling effects on behavior. Policies to protect location privacy evolved slowly, often lagging technology. Users often consented to tracking without fully understanding implications, lured by conveniences of location-based services. The bargain, free services in exchange for data, was seldom explicit, rarely negotiated, frequently regretted when consequences became apparent. Technical protections could limit tracking, processing location on device rather than sending it to servers. Differential privacy techniques that added noise to obscure individual movements while preserving aggregate statistics, zero-knowledge protocols that enabled services without revealing precise locations. But implementation was inconsistent. Many services required precise location for functionality, negating privacy protections. Users lacked expertise to evaluate privacy claims, to configure settings appropriately, to understand when location was being shared. Defaults mattered enormously, and defaults typically favored service providers over users. The environmental footprint of satellite systems included launch emissions, orbital debris, satellite manufacturing impacts. Each launch burned tons of propellant, releasing combustion products into the atmosphere. The accumulation of satellites in orbit created collision risks, potential cascades where one collision created debris that caused others. Deorbiting satellites at end of life was standard practice, but not universal. Some satellites failed before they could be deorbited, remaining in orbit indefinitely. Tracking these defunct satellites, predicting close approaches, maneuvering active satellites to avoid collisions, consumed resources and added operational complexity. The manufacture of satellites and receivers required rare earth elements, energy-intensive processes, materials with significant environmental costs. The disposal of obsolete receivers added to electronic waste streams. The system's benefits, enabling efficiency in transportation and agriculture, reducing emissions through optimization, offset these costs, but did not eliminate them. Life cycle analyses attempted to quantify net environmental impacts, comparing benefits against costs. The analyses were complicated by system boundaries. Should benefits of all applications be credited to the satellite system, or only those uniquely enabled by it? Should manufacturing impacts be allocated per user, per satellite, per position fix? Different assumptions led to different conclusions. What seemed clear was that the impacts were not zero. The continued expansion of satellite systems and receiver deployment had environmental consequences that deserved attention alongside benefits. The international cooperation required to manage satellite navigation was extensive, but sometimes strained. Frequency coordination prevented interference between systems, required agreements on power limits, on signal structures, on orbital slots. Compatibility and interoperability were negotiated, allowing receivers to use multiple systems seamlessly. But strategic competition also influenced decisions. Some nations designed systems deliberately incompatible with others, preventing adversaries from easily using their signals. Others made signals freely available, seeking to establish their system as global standard, gaining soft power through technological leadership. During conflicts or tensions, the availability of satellite navigation to adversaries was reconsidered. Systems were designed with capabilities to deny service regionally, to degrade accuracy in specific areas, to provide differential accuracy to allies versus others. These capabilities were rarely used openly, but existed as strategic options. The norm that satellite navigation should be freely available globally was strong, but not absolute. Users in disputed regions sometimes found service degraded, signals jammed during periods of tension. The systems, though ostensibly civilian, retained military origins and military priorities when security interests demanded. Looking forward, the positioning technology faced challenges of increasing demand, evolving threats, emerging alternatives. User expectations for accuracy, availability, reliability continue to rise. Applications like autonomous vehicles required performance exceeding what the basic system provided, driving demand for augmentation. Threats from jamming and spoofing motivated development of more robust signals, of authentication mechanisms, of receivers that could operate in contested environments. The cat and mouse dynamic between denial technologies and anti-denial countermeasures continued, each advance prompting response. Alternative positioning technologies explored different approaches. Terrestrial systems, using cellular networks or dedicated beacons, offered potential for indoor positioning where satellite signals did not penetrate. Optical positioning, using cameras and computer vision, provided complementary capabilities. Inertial sensors continued improving, extending the time they could provide accurate positions without external reference. The integration of multiple positioning sources, satellite, terrestrial, inertial, visual, into hybrid systems offered redundancy, improved accuracy, better coverage across diverse environments. But integration required sensor fusion algorithms, calibration across different coordinate systems, management of complexity that challenged designers and users. Whether satellite positioning would remain dominant or become one component among several depended on how these technologies matured, on economic factors, on whether applications demanded capabilities beyond what satellites provided. The educational challenge of a technology that worked invisibly was significant. Few users understood how positioning worked, what assumptions it relied on, what could cause it to fail. This lack of understanding created brittle dependency. When the technology failed, users were helpless, unable to troubleshoot, unable to fall back on alternative methods. Teaching the principles of positioning, trilateration from distance measurements, the role of time in determining distance, the sources of error and how they were mitigated, could foster better understanding, more informed use, greater appreciation for the engineering complexity hidden behind simple user interfaces. But such education competed with many priorities. Schools taught subjects deemed more fundamental. Users wanted tools that worked without requiring understanding. The path of least resistance was to treat positioning as magic, as a service that simply happened until it didn't. Experts who did understand the technology were a specialized community. Engineers who designed satellites and receivers, researchers who pushed accuracy limits, operators who maintained the systems. Their knowledge was deep but narrow, often focused on particular aspects rather than the whole system. Bridging between expert knowledge and public understanding required translators, science communicators, educators, technical writers who could explain complex concepts accessibly. The challenge was maintaining accuracy while achieving clarity, avoiding both oversimplification that distorted and excessive detail that overwhelmed. The history of positioning technology demonstrated that innovations often found applications their creators did not anticipate. The system was designed for military navigation, envisioned primarily for ships and aircraft, that it became integral to smartphones, that it enabled precision agriculture, that it synchronized financial networks, was not planned but emerged through entrepreneurial adaptation. This suggested humility about predicting future applications. The next generation of positioning systems, with better accuracy and availability, would surely enable uses not yet imagined, would solve problems not yet recognized, would create value in domains not currently connected to positioning. But it also suggested caution about assuming technology would solve problems, about technological determinism that saw innovation as inherently progressive. Positioning enabled beneficial applications, but also enabled surveillance, enabled tracking, enabled dependencies that created vulnerabilities. The value was in how humans chose to use the capability, not in the capability itself. And so the satellites circle, 24 of them always in view from most of Earth, broadcasting their timed messages, enabling billions of position fixes daily. The system operates quietly, largely unnoticed, except when it fails, maintained by teams who ensure satellites remain in orbit, clocks stay synchronized, signals continue broadcasting. In control rooms, engineers monitor telemetry, plan orbital maneuvers, upload navigation messages. In factories, technicians assemble receivers, test them against simulated signals, package them for integration into devices. In offices, software developers write positioning algorithms, debug failures, optimize performance. The infrastructure is vast, distributed, the product of decades of development, the work of thousands of engineers and scientists and operators. It represents a particular approach to the navigation problem, precise timing from orbit, global coverage from a constellation, open access to signals, an approach that succeeded beyond initial expectations, but faces ongoing challenges to maintain and improve. Users benefit largely unconsciously, their devices acquiring position, displaying it on maps, routing them to destinations, recording their movements. The technology has become ordinary, unremarkable, noticed mainly in its absence when signals are blocked or receivers fail. Yet the achievement remains extraordinary, that a device in your pocket can determine its position on a planet 8,000 miles in diameter to within several meters, that it can do this in seconds, that it works anywhere on Earth, that the service is free to users. This represents a confluence of physics, engineering, policy, economics that was not inevitable, that required decades to develop, that continues to evolve. the future of positioning will be written by decisions made now about satellite modernization, about spectrum allocation, about international cooperation, about privacy protections, about integration with other technologies. These decisions will determine whether the next generation of systems serves humanity as broadly as the current generation, whether they extend access to underserved populations, whether they address emerging needs while managing risks. The challenge is maintaining the public good character of satellite positioning while funding continued operation and improvement. The temptation to restrict access, to charge for service, to prioritize some users over others exists, but conflicts with the principle of universal availability that has been the system's foundation. Resistance to these temptations requires continued commitment from the nations operating satellite systems, recognition that the global benefits of free access exceed the costs of provision, that the positive externalities, economic growth, safety improvements, scientific advances, justify public investment. The alternative trajectories, fragmented regional systems, proprietary services, degraded free tiers alongside premium paid tiers, would diminish the utility, would create digital divides, would lose something valuable in the pursuit of cost recovery or strategic advantage. On a cloudy night, you cannot see the satellites. They orbit in darkness, too small and distant to reflect enough sunlight to be visible even when conditions are favorable. But they are there, their signals penetrating clouds, reaching your device, enabling it to determine where you stand. The signals are faint, weaker than background noise, but they are also persistent, continuous, carefully structured to be extracted from the noise through patient processing. They carry timing information, ephemeris data, corrections, everything needed to compute position. Your receiver listens, correlates, measures, calculates. It solves equations, applies corrections, estimates uncertainty. Within seconds, it displays a position, a point on a map, a latitude and longitude and altitude. The answer looks simple, certain, but it encodes the work of satellites in orbit, of clocks beating nanoseconds, of signals traveling at light speed, of algorithms untangling measurements into meaning. This happens billions of times daily across every continent, in cities and wilderness, on land and sea and air. The cumulative result is a world where location is knowable, where navigation is simplified, where position has become a utility as fundamental as time. We take this for granted now, as we take many infrastructures for granted, until they fail, until we realize our dependence, until we confront what we would lose if they disappeared. Positioning is not food or water or shelter, not survival needs, but modern life, as it has evolved, depends on it in ways both obvious and subtle. Losing positioning would strand travelers, delay shipments, disrupt communications, destabilize power grids, complicate countless activities that have adapted to its availability. We would cope, would rediscover alternative methods, would adapt, but the transition would be disruptive, the loss significant. This makes the system critical infrastructure, worthy of protection, of investment, of careful stewardship. It also makes it a target of vulnerability in conflicts, a point of leverage in strategic competition. These realities shape how the system is designed, operated, and defended. The people who work in positioning, the engineers, the operators, the researchers, often speak of their work with quiet pride. They are part of something larger than themselves, something that serves the world, that enables countless activities, that makes life better in small ways that accumulate to significant impact. They troubleshoot anomalies, optimize algorithms, plan satellite deployments, write specifications, test receivers, monitor constellations. The work is often unglamorous, technical, demanding attention to detail and patience with complexity. But it matters, and they know it matters, and this sustains them through the difficulties. When satellites fail, when signals degrade, when users report problems, they respond with urgency, diagnosing issues, implementing fixes, restoring service. The responsibility they carry for a system that millions depend on motivates rigor, drives excellence, creates communities of practice with high standards. They also grapple with limitations, with budget constraints, with political pressures, with the gap between ideal systems and practical realities. They make compromises, accepting good enough when perfect is unattainable, balancing competing priorities, working within constraints they did not choose. Their expertise is specialized, hard-won, the product of education and experience that takes years to develop. As older engineers retire, transferring this knowledge to younger generations becomes essential, ensuring continuity, preventing loss of institutional memory. The international dimension of positioning reflects both cooperation and competition. Nations collaborate on frequency coordination, on compatibility standards, on scientific research. They share data, participate in working groups, publish openly about technical developments, but they also compete, seeking to establish their systems as preferred standards, to gain strategic advantage through technological leadership, to reduce dependence on other systems. This competition drives innovation, motivates investment, but also creates duplication, complicates interoperability. The ideal of a unified global system, managed cooperatively, available to all on equal terms, remains aspirational. The reality is multiple systems, each controlled by a nation or bloc, each with particular characteristics, each with strategic implications. Receivers that use all available systems benefit from this diversity, but the underlying fragmentation reflects geopolitical realities. Whether cooperation will deepen or competition will intensify depends on broader international relations, on trust between nations, on shared commitment to global public goods versus pursuit of narrow national interests. Positioning technology intersects with many other domains: telecommunications, transportation, energy, finance, science. These intersections create dependencies, where disruption in one domain affects others, where improvements in positioning enable advances elsewhere. The coupling is sometimes tight, where systems rely critically on positioning and have limited alternatives. Other times, it is loose, where positioning provides convenience, but alternatives exist. Understanding these couplings, these dependencies, is essential for managing risks, for ensuring resilience. System-level thinking recognizes that positioning is not isolated, but embedded in larger socio-technical systems. Optimizing positioning in isolation might create vulnerabilities elsewhere. Designing for resilience requires considering interactions, ensuring that failures do not cascade, that backup systems are truly independent. This perspective challenges the reductionist approach that focuses on individual technologies without considering their integration. It requires interdisciplinary collaboration, bringing together experts from different domains, facilitating communication across boundaries that often separate communities. The environmental sensing enabled by precise positioning contributes to understanding of Earth systems, of climate change, of natural hazards, monitoring ice sheets, tracking tectonic motion, measuring sea level rise, observing atmospheric water vapor, all benefit from positioning technology that allows instruments to know precisely where they are when observations occur. These applications often require accuracy, exceeding what standard positioning provides, using carrier phase techniques, long observation times, sophisticated processing. The data contributes to scientific knowledge, to policy decisions, to public awareness of environmental changes. The irony is that technology developed for military navigation now serves peaceful purposes, understanding and protecting the environment. This transformation from tools of war to tools of science is not unique to positioning, but illustrates how technologies can be repurposed, how initial applications do not constrain eventual uses. The scientific community's embrace of positioning technology demonstrates its utility beyond commercial and navigation uses, its value for questions about Earth processes, about fundamental physics, about the nature of space and time. Relativity, once an abstract theory, became practically important for positioning. Clock differences from gravitational and velocity time dilation had to be accounted for to achieve necessary accuracy. This marriage of fundamental physics and practical technology enriched both, providing tests of relativity while enabling applications that required its insights. The positioning satellites became experiments in general relativity, their clocks running faster than ground clocks due to weaker gravity, slower due to orbital velocity, the combined effect requiring precise calculation. As we move through this night, approaching rest, the satellites continue their silent vigil, broadcasting timestamps, enabling positions, serving a world that mostly sleeps. The system requires no human intervention to function, autonomously maintaining orbits, correcting clocks, broadcasting signals. Ground stations monitor, ready to intervene if anomalies occur. But the day-to-day operation is automated, the result of decades of refinement, of learning what can be trusted to machines and what requires human judgment. This automation is both strength and vulnerability. It enables reliable operation with modest staffing, reduces opportunities for human error, maintains consistent performance. But it also creates distance between operators and systems, making diagnosis harder when unexpected problems occur, hiding complexity behind interfaces that may be misleading. The balance between automation and human control is never settled permanently, but shifts with technology, with experience, with incidents that reveal limitations of either approach. Positioning systems are far from alone in facing this balance. It appears across industries, across domains, a continuing tension in technological societies. And so we arrive at the end of this exploration, having traced positioning from celestial navigation to satellite constellations, from mechanical chronometers to atomic clocks, from tools of military necessity to infrastructure of daily life. We have considered the physics, how knowing when it tells you where, how light speed delays encode distance, how 4 satellites overcome 3 dimensions plus time. We have examined the engineering, how signals are designed for extraction from noise, how orbits are maintained over years, how receivers process weak signals to compute positions. We have reflected on impacts, on how positioning changed navigation, enabled applications, created dependencies, raised concerns about surveillance and privacy. We have acknowledged the people, the engineers who design systems, the operators who maintain them, the users who benefit often unknowingly. The global positioning system and its international counterparts represent a particular solution to the problem of location determination, a solution that privileged global coverage, high accuracy, open access. Other solutions were possible. Some were implemented in parallel. None achieved the same ubiquity. This success was not preordained, but emerged from technical capability, policy choices, economic forces, social adoption. The system could have developed differently, could have remained military only, could have been commercialized with access fees, could have fragmented into incompatible regional systems. That it evolved into a global public good reflects decisions by those who controlled it, who chose to make signals freely available, who maintained service through changing political and economic conditions, who invested in improvements that benefited all users. This choice deserves recognition and preservation. Maintaining the public good character of positioning systems requires ongoing commitment, resistance to pressures that would privatize or restrict access, investment in modernization without conditions that would exclude populations or applications. The satellites orbit on, indifferent to these concerns, executing their programming, broadcasting their signals. They are machines, doing what machines do, enabling what their designers intended and much they did not. The meaning of their broadcasts is constructed by receivers, by algorithms, by human interpretations of the positions computed. The coordinates displayed on a screen are not inherently meaningful. They become meaningful through context, through use, through connection to human purposes. Navigation is not just knowing where you are, but knowing where you want to go, choosing paths, making progress toward destinations. Positioning provides the first piece, where you are, but the rest remains human, requiring judgment, decision, action. This division between what technology provides and what humans must contribute is fundamental. Technology can inform, can enable, can constrain, but it cannot replace human agency, cannot make decisions about values, about purposes, about what matters. Positioning technology tells us where we are on Earth, what we do with that knowledge, where we choose to go, what destinations we pursue, what paths we take. These remain ours to determine. And so, the narrative of this assembly comes to its quiet conclusion. Whether you are still awake, or whether you have already drifted into a deep and peaceful sleep, know that you are exactly where you need to be. The world is vast, but tonight, its systems are simply the backdrop to your rest. Thank you for joining me here at Quietly Made. Rest now. Join us again tomorrow. Good night.